Excited to share with you. I'm excited to share some of the work my lab has been doing here at the University of Hawaii, applying machine learning and AI tools to the sciences. So if you haven't visited University of Hawaii, I would definitely invite you to come, especially if you're ever on vacation here on Oahu, because we're only 2 miles from Waikiki Beach. Um, you can basically walk there from Waikiki, which is the big tourist area and one of the best surfing spots in the nation. And the university is shown here. It's right by these great mountains for hiking. And the specialty of the University of Hawaii is oceanography, astronomy, because we have access to these telescopes on the island. Geosciences, we have all these active volcanoes on the Big Island. And biology, it's kind of a unique place. So I like to tell students that Hawaii is a playground for data science, and I'm part of this data science initiative on campus where we try to use all the latest tools from AI and machine learning and collaborate with people in these other departments. So I'm going to share a little bit about some of the work my group does on campus here at the University of Hawaii. So I wanted to start off by talking about what's happening in artificial intelligence, especially with generative artificial intelligence, and kind of highlight the things that I see are the most important innovations in the last couple of years. And then I'll talk about how my group is applying this to weather forecasting with AI and analyzing satellite data for remote sensing. So a big new buzzword in artificial intelligence is generative artificial intelligence. And this is the idea that AI can now create text, images, audios, music, all these really high dimensional data things that we used to think were science fiction. And there's been a lot of progress on this recently. So if you go to a company called Midjourney, for free, you can type in a text description of an image you want, and it'll generate a very realistic image or a cartoon image if you ask for that. So here is an example. If you type in, a camera hyper realistic photo shoot of an Easter bunny riding an alligator in Florida, it might give you something that looks like this, which is, probably not an image that the model saw in the training set, but it's able to generate a pretty realistic image that would be hard to identify as a fake AI generated image. And then another thing that's happening are these foundation models where you can go online and download a big AI model that performs some task for you, like computer vision or language processing, and you can kind of adapt that model to your own purposes. So you can fine tune the model to perform some computer vision task, even though the model was trained on other data by other people. And that, most of the people working in AI these days on applied problems are using this idea of downloading a foundation model and then transferring it to their problem instead of training their own models from scratch. And that's super useful in practical terms. So, the, 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 the core engine that's driving a lot of these AI systems these days has actually been around for a long time. That's this idea of deep learning with a neural network. So you have this artificial neural network model, which can approximate functions. It takes in some high dimensional input X, such as an image of a handwritten digit here, and you give it some target output for each input example, and you learn to approximate this function f of x. So the advantage of artificial neural networks is that they scale really well to big data compared to some other machine learning algorithms. They're modular and flexible. You can kind of design a neural network architecture that captures symmetries or properties that you want. And that makes them useful general purpose tools for all sorts of things. So this idea has been around for a long time, but when you apply it in these new, when you apply it to really big data sets, we're able to get very interesting results. So in natural language processing, we have these new ChatGPT language models. The idea for this has actually been around for a long time. So the way these models are trained are you have a bunch of text, you treat the text as a sequence, and you train a model to predict the next word. So Claude Shannon had this idea back in 1948, and he actually wrote a paper, in which he generated sequences from a language model just by generating the next word one at a time. But now we're doing the same thing for ChatGPT, except we have these big neural networks, which are much more powerful than the simple probabilistic model that Claude Shannon was using. He was doing all the calculations by hand. Now we have big GPU clusters that can crunch a bunch of numbers and learn from millions of text documents. But the basic idea is the same. It's this autoregressive model where we have some high dimensional sequence of data, and we train a probabilistic model in which we predict the next word one at a time. At the same time, we have new models for image and video generation. So these image models, you can type in a description of an image you want, such as the cat in the hat eating a burrito, and you plug this into a neural network, and the neural network can generate images that meet this text description. And it won't just generate one image, it'll actually sample from a distribution of all images. And so you can generate an arbitrary number of samples from this learned distribution over all the images of cats in the hats eating a burrito. So this is another form of generative AI. And I think the key point that I want to emphasize here is that, previously when we thought about supervised learning in terms of classification or regression, the output of the neural network was a single number or a single class label. And with these new generative AI methods, you're actually outputting a probability distribution over high dimensional data. So the model that we're learning here is actually a probability distribution. What is the probability of this image given the input X, which is the text description? And that's a key fact that I'm using in some of the applications that I'm going to talk about. So what can AI do for science? Well, science is all about modeling relationships between variables. If you think about your high school physics class and you learn these equations, F equals ma, these are relationships between different variables that describe the world. But if you have ever studied biology, you know that there's tons of stuff going on in a cell, and it's really difficult to keep track of all the variables. And many of these relationships that we want to model are probably too complex for humans to discover on our own. So artificial intelligence and machine learning is all about learning relationships between variables automatically. And so I think of AI and machine learning as a new set of tools that we can use to automate this process of science. And of course, a lot of these models are going to be wrong, but many of them are going to be useful for the types of things that we want to do. And this has a long history. So Gauss, who's this very famous mathematician, back in the year 1800, invented linear regression in order to do astronomy. Um, and linear regression has been the workhorse of science and industry ever since, for hundreds of years. So this is kind of a clean extension of the early work in science where we can build statistical models from data to do the science that we want to do. So whenever I give a talk on AI for science, I like to highlight that there's kind of 4 different types of applications that I group a lot of these applications into. Supervised learning, simulation-based inference, where you're combining computational simulations and machine learning, dimensionality reduction, and active learning. And today I'm going to talk mostly about these 2 categories where we're doing supervised learning on sequence data and dimensionality reduction with deep learning. So I'm going to talk about AI for weather forecasting now. And to start, I just want to give a brief description of how weather forecasting works currently. So if you go to weather.com or any other weather site, the data, the forecast you get actually comes from a government service called the National Weather Service. And these big simulations of the Earth's atmosphere are run on these government supercomputers that simulate all the variables that are important for weather. Every hour they run these simulations, and they incorporate observations from all over the globe to update the results of those simulations. So this is a very computational, expensive process, and really the resolution is limited by the resolution of the simulation. So, they take the entire globe, they chop it up into a bunch of grid cells in 3 dimensions, and then they model these variables and run it through a physics simulation to predict what's going to happen 15 minutes in advance, an hour in advance, 2 weeks in advance. So this is what's called a physics model of the weather systems in the world. And what's happening over the last couple of years is that people are trying to replace those expensive physics simulations with artificial intelligence models. And there's been a lot of progress in this, and people have showed that you can actually get better results faster in a lot of different situations. So the idea here is that you can train a machine learning model on historical weather to learn the dynamics of this atmospheric system. And you can combine data from multiple sources. And so a lot of the research in this area is using different data sources to try and build these models. But the idea is very similar to a language model like ChatGPT in that you're taking a couple of time steps of a weather system and you're predicting in advance what's going to happen in the next time step. So this is an autoregressive model, just like the big language models that are used. And so we do have some nice historical simulations. We have like these nice reanalysis data sets which combine the physics models with actual observations. They're actually like a revised history, which is actually better than the current forecasting system. So there's hope that these autoregressive models could actually incorporate more information than just the physics. So they're potentially better than the physics models that we currently use, and faster. So there's a bunch of efforts to do this from big companies and government labs. I've been kind of focusing on Hawaii because Hawaii is a nice way of testing some of these methods. Um, Hawaii is in the middle of the Pacific, so it's surrounded by ocean, and clouds travel kind of steadily across the ocean. But then there's these big mountains on the islands of Hawaii, which block the clouds and create all these little eddies and currents. And so, on the eastward faces of the mountains here in Hawaii, we get a lot of cloud cover and a lot of rain. And then the western side of the islands tends to be very dry, and we have all these microclimates. So on the big island of Hawaii, I think we have every microclimate except one. Um, it's very diverse. So statistical methods are appropriate for the Hawaiian Islands, especially appropriate because we can collect a bunch of data in a very small area here and use them to build statistical models. And the physics models fail miserably on the Hawaiian Islands because the grid cells of the computer simulations are much too big to capture all the variability here in the islands. So one of the things we've been doing is taking satellite data. This is the GOES West satellite on the left here. The resolution is 0.5 kilometers. And the cadence is actually 10 minutes for these images. So you can really capture all the variability on the island here. You can see on the right side, there's a mountain range going down the center of the island, and all the clouds get trapped right here on the island. And there's tons of rain on the rainy side of the island, but it's very dry over here. So one of the things we've done is we've built these autoregressive neural network models that predict 10, 20, 30 minutes into the future what the cloud cover is going to be. And one of the ideas that we have for using this model is to predict when there's going to be a bunch of clouds covering the solar panels. Hawaii actually has more solar power generation per person than any other city in the US. We get a lot of solar energy, and the energy prices are very high here, which incentivize people to install solar panels. But it causes a lot of problems for our electrical grid because we see a huge spike in energy demand whenever a cloud covers the solar plants here. So we've showed that we can do really well in predicting solar, both on the short time frame and about a day in advance. The Department of Energy has actually been running these competitions for solar forecasting, and my student and I started a company called Nimbus AI to compete and try to commercialize this solar forecasting product. So we won a competition in 2022, and then in 2023 we were able to win a forecasting competition for the Hawaii site, but we failed on the mainland sites, which just goes to show the differences between Hawaii and the mainland. And so, I've been focusing on Hawaii because it's a nice, small, manageable region to kind of test some of these ideas. But there's a bunch of other research groups, including groups from Google, Baidu, NVIDIA, and Microsoft, who are using these ideas to develop weather forecasting platforms. So it's a very exciting time. There's the limitations of this method is mainly that we don't have enough data to train really big models. We still have to limit the size of our neural network models. This isn't the same thing as ChatGPT, where you have millions of documents. Uh, you know, at best, we have a few years of really good high resolution data that we can use for these models. So that's kind of a limitation currently, but in the future, we expect to have more data. The other big limitation of these models is that if you train an autoregressive model to do forecasting in advance and you apply it iteratively to your prediction, so if you use the output of your 10-minute prediction and plug that into your model to make a 20-minute prediction, and then repeatedly plug that in, what happens is that your model predictions tend to regress towards the mean. And so it's, in a language model, you sample a word and you don't have this regression towards the mean problem. You have other problems, but it's kind of a statistical problem that you run into with autoregressive models. And so my group has been thinking about ways to address this by being more probabilistic with the way we treat these predictions. And so the next thing I want to talk about is how we're using diffusion models, which are these image generating models, to get more realistic predictions on longer timescales. So I'll give a brief introduction to diffusion models. So if you want to generate an image, it's a high dimensional sample similar to text. But if you use the same idea as text, what you end up with is something where you're predicting individual pixels in an autoregressive manner. So this is from a paper in 2016, which used this method to generate an image generation model. So here's the original images. The authors occluded half of the pixels, and then you can predict pixel by pixel using an autoregressive, like a recurrent neural network, to fill in the rest of the image. And you can generate many samples like this, similar to how you can get ChatGPT to generate multiple answers to the same query. So this works pretty well, except it's very slow because a full-size image will have millions of pixels, and predicting pixel by pixel is kind of a messy process. So one of the new ideas that's come out in the last couple of years is the idea of a diffusion model, or a score matching diffusion model, where you produce an image by iteratively denoising a random image. So the input to the model is a sample from a high dimensional Gaussian, which just looks like a random blob here. And you run this through a neural network, which gives you a slightly denoised version of the image, and you repeat this process multiple times until you end up with a sharp, clear image. The way this is trained is you take a standard image from your training set, and you add Gaussian noise to it, and then you train a model to try and denoise that image through a sequence of steps. So it's easy to generate training data. This is an unsupervised learning problem. And you use a UNet to learn this denoising process. So I'm skipping over some of the details, and there's a lot of mathematical work that shows why this works. But the end result is that you can generate samples through this denoising process pretty efficiently. It's not as efficient as a GAN or a VAE. It requires a lot more computation to generate these images, but you end up with very nice, crisp images, and it's kind of taken over the process of generating images in the last couple of years. And there's also some nice work showing that in terms of probabilities, this is a much better probabilistic model than something like a GAN. Um, so you're actually learning a good approximation to the distribution over all images. So this is just a diagram showing, in terms of the architecture, how does this relate to other image generating models like GANs or VAEs or flow-based models. And the key here is that diffusion models require a lot more computation during the generation step. But I think this makes a lot of sense in terms of gradually making decisions about what the image should look like and forming the image through an iterative process rather than just in one quick shot. So one of the applications of this is super resolution. So you can start with a very low resolution image like this 64 by 64 image. You run it through a conditional diffusion model where the input to the model is this low resolution image plus this Gaussian noise image. And the output after running through this UNet multiple times is a high resolution image. You can cascade these models to generate higher and higher resolution models. This is an example from Google Imagen. And super resolution is super useful in weather and climate science. It's actually known as statistical downscaling. So, what are the dangers of using super resolution in the sciences? Well, there's lots of dangers. This is from a Nature paper kind of advertising the dangers of using super resolution models for science. In microscopy, you might have some very low resolution image, and you might be able to train it to give you these nice, sharp, crisp images of the inside of a cell. But you have to make sure you understand that this model has been trained on a certain set of data, and it will kind of interpret all the data you give it in that light. I thought this was a very nice example. I plugged this image into Midjourney to get even higher resolution images and got some cool results, but these are not scientifically useful. So one of the things I've been doing here at the University of Hawaii is applying this to different applications. This idea of super resolution, being careful that we're actually looking for real applications that can be used. One of the things that we've tried doing is taking a 3D optical body scan and predicting the bone structure of a person from these DEXA image scans. And so this seems to work pretty well. But what I'm really excited about these days is using this idea for weather forecasts and getting high resolution weather forecasts. So the standard weather forecast for Hawaii is at this resolution, 25 kilometers. This is the global forecasting system that, if you go to weather.com, you'll see something like this. So the island I live on, Oahu, is only 50 kilometers across. And so this resolution doesn't capture all the variability in my neighborhood. But if I look at the satellite data that I showed you, this is 5 kilometers. This captures a lot more of the variability. And so what I'd like to do is combine the statistical information from this satellite observation data with the forecasting system that's output from the government. And so what we've done is train a conditional diffusion model, which takes in the GFS forecasts for tomorrow or 2 weeks from now. And we can super resolve that to get samples of what the cloud cover will actually look like given the GFS forecast. So on the right here, I'm showing 25 different samples of possible cloud covers given the forecast. If the GFS forecast says it's going to be cloudy, this will show me what those cloud patterns might look like. So we're using this, the same idea as Imagen, where we're doing this using a cascaded model. And we can show that, if we take the average of all the predictions or all the samples of the cloud cover, the error goes down if we look at the mean of the cloud cover. So we can do this for historical data, but also in weather forecasting. So here's some examples of, on the left, we have the ground truth cloud pattern over Oahu. Here's 5 samples from the cloud cover distribution. If we take the mean of 45 samples, we can kind of see that the prediction is that we'll have a lot of clouds over the mountains, which we expect. And then the ERA 5 here, this is basically the coarse resolution forecast from the government simulation. And our forecast is much better because it's much higher resolution. I'm going to skip over this a little bit, but we're doing similar things with climate data because the way we forecast future climate is very similar to the way we forecast weather. We run these big numerical simulations for 1,000 years in advance under these the condition of global warming. And one of the things we're interested in here in Hawaii is how future climate is going to affect the amount of water, drinkable water we have on the island. So what we're trying to do is predict the amount of monthly rainfall under these different climate conditions. And we're using the same kind of statistical downscaling super resolution models to do that. This is a map of all the rainfall data, weather stations around the islands that are able to collect rainfall data. And we have a partnership with the geographers here at UH, and we're taking all that data and trying to predict future rainfall. So we have some ideas for how to use deep learning for this. I'm going to kind of skip over this. We haven't submitted a paper, but I can show you this. This is, so the traditional method that's used, basically future downscaling using statistical methods and then using Gaussian processes to kind of interpolate between the rainfall stations that we have, gives you kind of this blurry image like this. But our neural network model is able to incorporate more information, and we're giving these very high resolution maps. So we think, we have some results that show that this is slightly more accurate than the traditional methods. And so we're publishing a paper on this soon. Okay, so the last thing I want to talk about is representation learning for remote sensing. And I just want to highlight again that one of the big advantages of deep learning, one of the big advantages of deep learning is that we can train these foundation models and then transfer them to new applications. So this is a very common thing. We published a paper a couple of years ago applying this to breast cancer. We have a collaboration with the University of Hawaii Cancer Center. But this is not something that we do exclusively. Lots of people are doing this. So you can download a big image classification model that was trained on cats, dogs, airplanes, these ImageNet classes, and you can fine tune the model on your own data set that you have labeled. In our case, we have these mammography images, and we're trying to predict cancer versus no cancer. So you take this pre-trained model, you chop off the top of it, and you initialize a new small neural network on top that you fine tune on the limited data that you have. So this works amazingly well, even though these images are very different from the mammography images. Um, a lot of the same features turn out to be useful. You know, this foundation model has learned about textures and colors and objects, and you can use that feature space to do cancer classification. But obviously, if we had millions and millions of mammography images, we would prefer to train our own classifier using that labeled data set. The problem is we don't have enough labels to really do that. So one of the things that we've been working on is for a lot of these science applications, we really want a model that knows that is tuned to the type of data that we have. And we've been working with some oceanographers who have access to millions and millions of satellite images. So this data set we have is 10 million SAR images. So SAR stands for synthetic aperture radar. There's this European Space Agency mission which collects global images of the world's oceans every 6 days. And the images kind of look like this. Each pixel is about 4-meter resolution. So you can see things like boats, mainly from the wake left by the boat. These are icebergs here. The satellites actually emit microwaves down to the surface of the ocean, and they travel through clouds. And so you can actually see rain patterns by the amount of roughness on the sea surface. So the microwaves are invisible to the clouds, but you actually see the rain based on the roughness of the sea surface. And then down here we have a biological slick, which is some like phytoplankton on top of the ocean. So this is a huge resource, for monitoring the world's oceans. But the oceanographers have trouble making use of all this data that's being produced. So my student has been working on building a foundation model to help analyze SAR satellite imagery. So the goal is to learn a function that maps similar images to similar points in an embedding space. So that I forgot to mention, so the 10 million images we have, there's no labels. So we want to learn some useful representation of the data, and we want to do dimensionality reduction on this data without a big set of labels like we have for the ImageNet model. So we're using this contrastive self-supervised learning method, and the basic idea is that we augment the images with changes such as rotations or reflections, and we run those augmented images through a model, and the embedding that we get should be the same if we started out with the same or similar images. But if we start out with different images, the embedding should be different. And so basically we're clustering images in this embedding space. And there's a whole bunch of contrastive self-supervised learning methods to do this. So my student has done this for these 10 million SAR images, and then for a bunch of use cases, we have these oceanographers doing these labelings of different phenomena that they observe in the images. And then we can use this supervised fine-tuning from the self-supervised pre-trained model. And the goal is to get better predictions with less labeled data. So we have some really nice results showing that this works. Here we're comparing a classification problem. This is the AUROC of the classification task. And we're comparing a pre-trained ImageNet model versus this self-supervised learning model trained on 10 million SAR images, and we get better performance when we're using this our own foundation model. These are more results showing that you need less labeled data in order to get the same performance with this SAR foundation model. And the different tasks that we showed that you can use this for different tasks. So in this task, we're predicting the wave height from the image, which is important for tracking, the waves we use for surfing as they travel around the globe. So, we get an RMSE of 0.56 using our foundation model, and then if we do the same thing with a model trained on cats and dogs, we get worse performance. Another nice thing that you can do with this is once you have a dimensionality reduction method, you can use it to search images. So, oceanographers have this giant database of 10 million images, but they can't look through all those images, right? But if they find some phenomenon of interest, so you can take this image and you can query this database of 10 million images to say, what are some images that look like this image? If you use an ImageNet model, it doesn't really know the properties of this type of image, so it gives you a bunch of random results. But if you use our model, you end up with images that have the same type of phenomenon. So these are all iceberg images here. Hello. Oh, sorry.
Early.
Yeah, so that's a summary of my talk. And I'd just like to thank all my students. And if you're ever in Honolulu, come visit the University of Hawaii, which is down here by the screen, and up here is Waikiki. And there's lots of great hiking and stuff to do right around the university. Thank you very much.